Why have I put assignment 2 with assignment 1? Well, basically it all comes under the same topic of contours. Okay. Right. As I said, we'll talk about contours. We'll do a little class exercise in here for eyeballing as well at the end of this. I'll point out a couple of things that will be questions in the test. I'll talk about a little bit about the characteristics of contours as well. Okay. But as you can see up there, we're going to start with a few things to point out from last week. Some of you have decided to join this week for different reasons. Could be enrolment reasons, it could be all sorts of reasons, but you did miss a very vital week last week on exactly what I'm expecting on your existing site plans. Just as a little bit of a revision, you've been given a file. You're expected to put a title block and a logo in that file. You're also expected to change the layers and get things coloured by layer. If you're not sure what by layer means, you can highlight everything and go up the top right, and where the colour box is, it should say by layer. In fact, the line type should say by layer as well. One of the important bits that I didn't say last week is that if you select a line type, say for example a centre line type for the pipe, that is not your job done. That's the start of your job. Job done is when you pick the LT scale that works. Now this time round you've got a little bit more of a difficult job, because you're going to have 2 or 3 line types, and one LT scale has to fit all 3 of them. So in order to do that, do not choose a line type with ACAD in front of it. You're going to have difficulties matching it up with the normal ones. Normal English type line types, hidden, centre line, dashed, hidden 2, dash 2, they are the line types that divides another one, or phantom. They're the ones that you should be using. Also, there was a tricky thing in inserting the when you do the print file, make sure you get that right. If you weren't here last week, you're going to have to buddy up with someone and make sure you don't stuff up your units, because you do that, you're on your path towards seeing me again next year. The other thing with last week is we talked about some things that are in the test. We also talked about how to calculate the text type. And we also showed how the main text type for the drawing is also the main arrow size. I explained to you that the information given to you in the first semester, like where we gave you the line offset, the text offset and all that for the dimension settings, I said to make them about roughly a third of the size of the text, the main text that you're going to be using. That's not the point, that's not the 7 or the 5, but the 3.5 millimetre text in layer. Why do I do it so you have to calculate it from layout? Because layout is what the client sees. Layout is the print that the client gets. The white space, the space that you print, that you get the text as text type on. So the client will say, I want a text type of 3.5, otherwise you're going to be sending me back to the opticians to get a different size pair of glasses so I can read it. Okay? Okay, that's fine, you're the boss, you're paying the bills, I'll make the text type 3.5. Your brain then has to calculate it according to the scale in model space, and it's very common. It's not uncommon for that. What is common is the likes of, let's say, a survey goes on site. They do a good survey, nothing wrong with the survey at all, but they're told to put some labels on it. So they just use the default in AutoCAD, and they put some labels on that, wetlands, seat, retaining wall, and then they print it and send it to the client. But that text type is so small, the client can't read what the hell they are, or it's so big it's taking up the whole drawing. So from a survey perspective, usually you're drawing in model space on top of your survey, so you've got to figure out what is the right size text. We've all seen drawings that have got horribly big or horribly small text. That's not what I want you guys to be doing. We also talked a little bit about the possibility of going into lockdown again. Let's hope that doesn't happen. I'm more of a positive than a doom and gloom person. But if it does, the best thing you can do is to try and future-proof yourself by having a computer that will still handle 2020 back at home. Some of you had issues in the first semester. Some of you are coming in here from 2019. Just check that your species are up to scratch for that. Or if you have a home computer or one you can borrow. Did it say late? I'm going to check that. Okay. So this week's notes, I'll make this available after class. And you'll see why towards the end. There's not much. There's more background material than anything else. So the contour is an imaginary line on the ground surface connecting all levels of equal elevation. So in other words, you could probably walk around a contour and eventually you'll end up back where you are. Might take quite some time. It might be off the drawing. It might be walking around Mount Eden at the same height, but eventually you'll get back to the same position. Something to always remember. The contour interval is something that you don't always get. And that is really dependent on the type of survey. So for example, if you're going to do a motorway, you want the surveyors to go out there and do a really good job of a survey with an accuracy of around about 10 centimetres. Okay? Why? Because you're doing 100 to 120 kilometres an hour. You're doing horizontal curves which have spiral curves leading into them, which are all calculated very accurately on motorways so cars don't go off the edge. And you can't calculate that sort of accuracy using that sort of data. You guys are going to do that on a highway engineering with a survey that's, say, only accurate to 100 mils. Okay? So they've got to come right down to 10 mils for that type of thing. If the surveyor is asked for data for a proposal of, say, 30 metres of road from, say, Warkworth, 30 kilometres of road from Warkworth to Wellsford, it's different altogether. It's a long length, probably a small piece of paper it's being printed out on to give to different people as a proposal. You're not going to do contours to every 0.1 of a metre. You're not going to do it to a metre. You're probably going to do it to maybe 50 or 100 metres, just so you've got a bit of an idea of the terrain and where the road's going and where the cut and the fills are going. So it'll also give you a bit of an idea of the cost for earthworks. So the surveyors won't even go on site for that. They'll buy that data. Some of the data may be estimated with trees, the average tree height versus, you know, what it's been picked up from the sky. Then you'll get down to other things like, say, a gravel road to a wind farm at Raglan, where you can actually do it off aerial photography to the nearest metre in terms of contours. Because it's only a gravel road and you only got a digger out there and you just need to work out approximately where it's going to go, so you can just use a digger to form the gravel road. So once again, it depends on what you're doing. Here's another one, a bowling club, right? We're talking of not cricket, by the way, for the Indian students here. This is the ones with the old fellas like me bowl the ball along the carpet, you know, but it's a green grass carpet. That has to be pretty accurate. We're talking maybe down to 5 millimetres, or else of course the ball's just going to start rolling down and following the wrong course. We once had a team bonding thing here where they invited the top staff at Unitec to give our department a game of bowls. Just a side note, don't get the bias on the wrong side of the ball when the top person that's at Unitec is just on the court beside you, or whatever it's called. Put their ball right beside the little wee white ball, expecting to win. And also don't give it to Roger with the intention of trying to knock the hell out of the ball straight in front. My ball went, actually this has got nothing to do with the subject, but I knocked the boss's ball for six on a completely different bowling mat to what we were on. Consequently, he didn't talk to me for about 2 weeks. So yeah, no, it's important to get your levels dead right. And lastly, if you're looking at, say, the lunch area out there, where at Unitec, before you go into the hub, that needs to be down to about 10 millimetres as well, because it's drainage. You know, we don't want students walking through knee-deep water, because a surveyor's given a really inaccurate survey and the water's all banked up in one corner, okay? So when you're doing that, it may not look like something you need high accuracy for, but when it's pretty flat, like Christchurch, for example, that was a hell of a job to redesign all that after the earthquakes, because it's a flat city. You know, you get your levels wrong by this much, and you've got yourself a pond sitting in the middle of nowhere. So the contour interval is really important. I've put 3 questions in the test about that, with an example of a survey and the type of accuracy you should be looking for.
When you say contour interval, is that the distance between the lines?
It's not. It's the height interval. Okay,
Okay.
but looking in plan view, it is the lines that you draw on the plan. So, for example, if we did that proposal at say 1 metre intervals, contours, you're looking down, it would just be black, because there'd be so many lines on it between over 30 kilometres. Right?
Because they're really close together.
They're really close together, yeah. I've given you a survey with the intervals, all right? I'm just pointing out the fact that you don't always get that luxury, and particularly surveyors, because they're the first on site, and the client goes, a client typically will say, well, I don't know, just do it to whatever you think, right? Same with engineers. And you're going, oh, Roger never taught me that, he always gave me the survey interval, right? So it's like the scale of a drawing as well. You've got to pick the scale of the drawing that fits nicely on the size drawing. We used to always do A1s back in the day. We had a funny thing called a pen plotter, right? I'm just going back quite a bit here, guys. You probably weren't even born then. Used to pick up the pens. It was really cool to watch. And it would pick up another pen and do all the red, then all the yellow, etc. And that was a standard A1 sheet. And then the guys in structural were complaining because they go on a 7, 8, 9, 10-story building in Auckland, and they'd be on the roof trying to pull out these A1 plans with a good, decent blow on in the Waitemata Harbour, and they've lost the plans. They've gone, shh. Right, so laser printers came in shortly after that, because the original A4 printers were hopeless. They would leave stains all over the paper that you could not hardly read them, you know. But the laser ones came in, so then we had to correlate scales. So we would still do A1s, because councils still insist on A1s. They do, believe it or not. Most building sites, if you go into a house, there's a whole set of A1 plans sitting there, right? Because everybody's looking at them. But in terms of practical, a little A3s, you know, were perfect for going on site for most people. Sorry, digressed a little bit. Here's some examples here. I suggest you probably have a good look at that, the type of spaces one would use. There's the schematic up the top, 5, 10 metre contours, possibly as high as 20 or 50 actually, depending on the length. Characteristics of contours, once again also in the test. The interesting thing about contours from an experienced engineer's point of view, if you see contours that are evenly spaced, like this, then that means that is an even slope. So that's more likely what you'll look at when you, on your platform, coming down or going up from the platform, because it's a nice even slope of 1 to 1 or 1 to 2. So in plan view, you would immediately recognise that probably as man-made. Not always, but 99% of the time it's man-made. If you see contours coming in like this, it's not an American Indian arrowhead, it's actually either a valley or a ridge. So it can be either or. So don't automatically think, oh, that, I know that's a valley. It might not be, it might be a ridge. So little things like that on contours start to give you clues. Another one, if you start seeing contours that are sort of like this, don't automatically think it's Mount Eden. It may not be. It might be a hole in the ground. So interpreting contours is a very interesting skill that you eventually get to hang on very quickly. Another thing with contours is if we draw arrows at right angles to the contours, we can very quickly work out, now this is a simple example, but it's a bit like once I was at Eden Park and it was an All Black test and I was in the old terraces. Doesn't happen so much now. This absolute idiot from Waikato, I know that because they all have Waikato jerseys on, or Chiefs, got up and just for no reason hit the guy in front of him, right? And then he just sat back down in his seat, and it was the funniest thing I've ever seen because the whole crowd saw it, and the security guys turned up, and they're looking, and everyone in the crowd was pointing at him. So you saw you saw arrows like that, all pointing at the one person, and it was like there's this one person, he was sitting down there with his head like, you know, and they just all went and grabbed him and took him away, and that reminded me of this, because many times in my job I've had to do these arrows. Now that's a simple example, pretty obvious where you're going to put your drain, right? But it's not always obvious on a site that has contours all over it. You start putting directional arrows, bang. You can find out the exact position where you should be putting a drain. Little things like that are tips that you pick up in the engineering field and you start working out. It makes life a lot easier for calculations, it makes it easier talking to clients. The average client has a reasonable idea of things, but they want to be told exactly what they can and can't do.
But wouldn't there be numbers on the contour lines, and then that way you would see if that was lower than that?
Yeah, but that's how you do your arrows. The arrows always points at the next contour down,
Lower.
so to speak, lower. Yeah, so eventually you find the point that's best. See, in a situation where you do have a low contour, and then you see that might be 100, and you know that's the lowest, but there might be a 101 there and a 101 there. You might have a 102 coming in like that.
And you don't know which ones connect to each other.
No.
Yeah.
So by doing the arrow thing, eventually you find out that the low point's actually somewhere along here, but where along here? Not quite sure, and that's how you determine it. Contours should not cross each other. So if you see contours crossing each other, and that's one of my questions as well, you've either done something wrong when you've calculated it, and I do get students, they'll email me and say, oh, your spotlights are wrong, Roger. They're completely wrong because I keep on getting contours that are crossing each other. And if you do that, you've done something wrong. There is a rarity, I don't know if anyone's seen that movie Cliffhanger. Perhaps it's just a little bit before your time where they're holding on to the, who was it? The guy that can't talk properly, forgot his name.
Vin Diesel?
No, sorry. No.
Steven Seagal?
Remember I said he can't talk properly, or mumble. Sylvester Stallone, yeah. And he's hanging on to the cliff like this underneath, and the cliff kind of goes back underneath itself. That is a situation where contours do cross, but that's not. I don't know where that is. Probably somewhere in the Rockies, but it's definitely not New Zealand. That's not a question, by the way. And there's no half marks for getting that actor who can't act. And is not as good looking as Steven Seagal either, by the way. Not that I would know. Right. So, how do we calculate from spot heights that I've given you guys on the plans? How do we calculate our contours? Well, there are basically three methods. I talked about them briefly at the beginning of this lecture. There's the estimation one, which we're going to do a little exercise in a minute. There is the graphical one, which is where you get your calculator out and you start dividing the line up. And you mark on the line exactly where the point is that the contour crosses. And then lastly, the graphical one is where you use the divide command in AutoCAD. So you can see here, you've got a level A 51.5, a level B 50.6. You've got to find out where this 51 contour crosses. In order to do that, you can tell there is 9 nodes between there. So you divide it by 9, 1, 2, 3, 4, 5, 6, 7, oh, sorry, there should be 10 there, but there'd be 9 divisions. And then you count from 50.6, 50.7, 50.8, 50.9, and 51, okay? So by dividing, it's just a matter, once you've got those nodes on there, of counting to the right spot. And that was the command that I said was sort of halfway in between my nerdy students who will spend 15 hours on the weekend, and my ones that have got too much on their plate, which will spend 10 minutes estimating or eyeballing, okay? The only problem I have with using the divide command is when you're on site, you don't always have a CAD or something like that. So I will test you on your ability to do the calculation method. I'll give you an example on the board shortly of a calculation. It really isn't too bad, but it's just to do my assignment, you're going to have your calculator out for half the weekend, right? To do it by divide is a matter of going around each point on your triangles and dividing each line. And that's exactly what 12D does, by the way. It basically triangulates a site between the spot heights. I'll show you that in a minute. And then on each line, it'll determine where the contour crosses.
You know how that one was like that, dividing?
Yeah.
How do you know it's not like that?
Well, probably it's time to go back a bit here and let's show you what I'm talking about. So here's your answer to your question, basically. A little bit hard to see that because of the light. I'm not sure if I can turn that off. There's some lines drawn there. Can we have a light anyway? Yep. Is that good enough?
Better.
We were better?
Yep.
How's that? Okay. I don't know how good you guys can see, but there's lines here, right? Yep. I'll give you this file to look at once we've finished the lecture. So your answer to whether it goes that way or that way is determined by the next line. And yes, it's a bit jaggedy. And unfortunately, that's how I want you to do my assignment. But in the real world, what you can do is programs like 12D and Civil 3D is you click a button and it smooths it for you. And I guess in AutoCAD, if you did that with a P-line, you could right-click on it and make it a spline line, which is like a P-line that's been smoothed. I would rather you didn't do that because I'm going to be putting my template on top of yours, and that kind of yours will start looking like, you know, a blurred picture. It's not quite in focus. So if you just do it that way, you'll be fine. Here's the catch for those that are thinking, well, I've got one good friend that's good on AutoCAD, and we'll get him to do it all, and the 6 or 10 of us will just copy his contours. The triangles are determined by you. So there are other ways we could have done this triangle. For example, I could have gone from here to here, and then I could have gone from there to there. Albeit a bit different, but right? So whatever way you determine the contours is going to mean that these lines are going to be just fractionally different to the next person. So later on, we're going to be doing a long section next week, some cross sections a few weeks later. So the cross sections and long sections, the data will be slightly different between students, and it all goes back to how they've chosen to do this. So it's a little bit suspicious if everybody's chosen the same triangles. I've got a little thing beside my desk at home, it's called an alarm bell, and every now and then it goes off, okay? So if you do your own work, it's not a problem at all. The thing is, I have a saying called KISS. I don't know if any of you know that saying. Keep it simple, stupid is what it stands for. And when I do triangles, I keep it simple, stupid. Basically, there's no need to do a line from here down to the other point down here. Why not just keep it relatively simple like this to where the spot heights are? So the more simple you keep it, the easier it becomes. I get students and they'll go, oh, no, I'll draw a line here as well. I'll draw another one up to this one, and I'll do one over here, and it just is, the triangles are just absolutely everywhere.
What would be the advantage to doing it that way?
I guess the more triangles, the more accurate it is, but at the end of the day, the accuracy is only as accurate as the surveyor reading the 22.21 anyway. Yeah.
Would the easiest be to pretty much draw a circle around the whole outside and then work your way in?
Yeah, but I've added another little little mean thing to my assignment.
Thanks.
That's fine. There are existing contours. All right, so you need to join with a triangle to one of the existing triangles. Now, contours. There are existing contours. Existing contours, that spot height is the same all the way along. So say it's the 28.2 contour, then all the way along that contour is a 28.2. So to finish it, so for example, we've stopped here. So to answer your question, this might be where my spot heights end, but there might be a contour coming down here like this, stopping there. So you'll need to come up to that contour, and the level of that contour will be whatever the contour. So you're joining into a spotlight on the contour itself to finish the survey. All right. Not uncommon, but just a little bit of an extra there for you to think about. All right.
So the key is just to put your triangles from a spot height, and then you sort of work out.
Yes.
outwards, yeah.
Yeah, if we look at the assignment, which I can do now, you'll see exactly what I'm talking about. Some of you probably haven't thought about this at this point, but let's have a look at the assignment itself. Where are we? Here's one. It's a sort of a sketch. I can't open the drawing because this computer doesn't have AutoCAD, but I can open the sketch. So you'll see what I'm talking about right now. See that?
The blue dots are the spotlights, right?
Yeah, these dots are the spotlights, and you're given those on the survey drawing. But these points that come down here are contours. They are labelled.
Yeah.
So everywhere along there is, and I would suggest strongly you use the end of it. Don't come up halfway along it or something like that. You might start getting inaccurate results. Okay.
Didn't you say some of those spot heights will be wrong?
If you do, put it this way, I've gone through and changed them manually from a previous survey from about 2015 when it was a class exercise. So I said they could be wrong, and so if you find one and you think, hello, this does not look right, just like the spike, email me. I will make it, the whole class will find out about it because it's my fault. But just keep your eye on your emails. If something comes through saying the spotlight over by the tree or above the letter B is wrong or something, I'll email you guys and I'll tell you. At this stage, I think they're all pretty good. Okay, and these ones over here, which are on the wrong side of an existing contour, they don't need to be used at all. So they're kind of like another little tricky one that I put in there. Because they're on the other side of existing contours, you can't connect to them because you're going through a contour to connect to it. Just like you can't make a triangle from here to that contour because you're going through an existing one. You can only do it to that one there. Right? So be careful when you do your triangles, don't go through existing contours to another one way over here because that will place those ones in a fractionally different position. So you're kind of shooting yourself in the foot when you do that. Didn't expect to have to explain that, but that's cool, that's good. At least everybody's on the same page.
So, yeah, just to be clear, I know you said it already, but each one of those contours should connect to another one.
Yes.
On the
at
other
top.
side.
Yeah, so it's best to use the end point of one of those as a spotlight.
Do we have to use every contour? Or are we just like creating a triangle out of those?
If you need to create a triangle, yes.
We can, so you just use it if you need to create a triangle.
Yeah, well, where a point comes down like this, and you've done a triangle from there to there,
Yeah.
and you've calculated it's going to go to there, it's perfectly okay if it's nice and close just to draw a line like that. Okay? But in some cases, this might be way down here, and you're kind of got a couple of contours coming in like that, and you'll get there, there, and there. And okay, that might be alright, but that seems like you're going to have to do some calculations to try and perhaps do
Get another contour spotlight.
another spot height to get it a little bit more accurate. When I put my template on top, this is how I mark it. If it's really close to my template, it'll still be 2 marks. Okay? Which means that, in my opinion, not only have you calculated it, but you've got it pretty good. Right? If you absolutely stuff it up, but it's, it's sort of a bit blurred, you're more likely to get 1 mark. But you don't have to correct it for assignment 2. You can use your contours to do your long section and your cross sections, etc. And your earthworks calculations and everything else we're going to do. But there is a little proviso on that. If you've really stuffed it up, then I may have to give you some sort of model answer to work with to do your next stage. Okay? Even though they're connected, you shouldn't have to do an assignment a second time just to do assignment 2. For most of you, and probably 99% of students in the past, I've just let them go ahead to do assignment 2 with whatever contours they've done. They don't get marked down for it after in assignment 2. So let's do a little eyeball exercise there, mate. I want you on your piece of paper there to do 1, 2, 3 crosses. And from those 3 spotlights, interpret as best you can contours to the nearest metre. So we're starting simple. Shouldn't take too long. We're eyeballing, so you don't need to get out your calculator, you don't need to get out your scale rule. Just do 3 points and approximate where the contours are going to be. Okay, so moving along from that. The way how I would do this is I would mark out between the points a line and along the bottom. How many forgot to do that? And then I would mark on there where the various contours cross by dividing that line approximately in my head. And then it was just simply a case of joining each point up as it went through. Okay? Now, if you're going to do your contours by eyeballing, that's fine. You just draw the line and be done with it. So I would have, if I eyeballed this, I probably wouldn't even do that. I would have just drawn the line from here to here to here, from there to there to there, from there to there to there. Done. All right? Rough enough. Eyeballing. This is eyeballing, but being a little bit more accurate with the way I do it. If I was to calculate this, I would calculate that length and then divide it by 3, and I put a little mark on there. Now, if you're going to do it by calculation, put a little mark on the line and freeze the mark. When I open everybody's drawing, I thaw all the layers. If I see marks there, it shows me you've been doing it by calculation. That's really important. I get students going, I just spent 15 hours over the weekend and you gave me 1.5. Where have I gone wrong? I say, well, where you went wrong was you never put a mark there to show that you'd calculated it. Alright? So you've got eyeballing, no mark, calculation, a mark, and of course if you use the divide command it leaves nodes on your drawing. You guys have all had experience with that last semester. What did Ingrid tell you to do? Freeze the nodes or make them really tiny. So you'll need them fairly big so you can see them when you're drawing your contours, but of course when you present the drawing to me, really small. So that was an easy one. That was just a one of those sort of fun things to lead you into it. Now we're going to get a bit harder. 4 points, 19.2, 19.5, I'll go a bit closer to that for anyone that's finding it difficult at the back. You see that all right? So 19.2, 19.5, 19.0 and 18.7. At this point, I'm asking you to calculate every point 2. Which is like your assignment. Your assignment's every point 2. You get me in there as well? Okay, so we're going to have to move along with this because I've nearly breached my hour already, and I've still got to do another an example, 2 examples on the board. Okay, so you can't just do point 2. It's too tricky to do it by eyeballing. So what we do is we do it point 1s, and then we do every second one. Okay. So we do point 1s because that's easy to do, and we go between there and there is 3 of them, between there and there is 5 of them, between there and there is 3 of them, etc. And then of course, instead of doing every point 1, we just join up the point 2. So the 19.4, 19.2, 19.0 and 18.8. That is a very big clue for those that want to do eyeballing for the assignment. You kind of got to do point 1s first to get to the point 2s. Now we're going to do a calculation, and we're going to step it up a notch, and we're going to show you how to work out a distance to a contour by calculation. So we don't need, we'll leave that on the board at the moment. Then we'll come over here. So I'll just put a squiggly thing on here. Apologies for my squiggly thing, it could go either way. Let's put the contour coming through about, it's going to be a little closer to this end. So let's make this contour coming through here 101. 0.0, I'll just call it 101. And you're asked to find that value there, which is that distance. We'll call it X. And I will nominate a distance from here to here as being 20.25. I'll make it 2.6 because it's too much like the top one. Any idea how we can find X? So this is for my nerdy students who want to calculate everything perfectly on their contour. You got a bit of an idea? Yep.
You divide the 20.26 by the difference of the 101.25. Like the difference between it?
You find that the distance between 101.25 and 187,
Yep.
Are they coordinates?
No,
No, no, no.
they're levels, and this is a distance in AutoCAD. So in order to do it, you need to look at what's happening in elevation, which is goes way back to your distances between the contour intervals versus what's actually happening in elevation. So in elevation it looks something like this. Up here we have a value of 101.25. Down here we have a height of 100.87. Therefore that distance there is, do we have anyone with a calculator in the class? 13 and 28, 38? 0.38? 0.38, right? Coming in here at 101.00, what's that distance? 0.25? Can anyone remember doing that at the age of about 14 at school in mathematics? Equal triangles? Can someone give me the equation up the top for x? We're trying to find this distance here is 20.26 and this distance from there to there is x. So you've got two triangles that are the same with different heights. Can anyone give me the equation? So the height is 0.38 divided by 20.26 equals 0.25 divided by x. Correct. I would have given you a half a mark if you hadn't been doing this course for the 14th time. But I'm glad you learned something, okay? So basically it is 0.38 divided by 20.26. It's interesting, the people that laugh the most at that comment, I usually see them next year. I'm not terrible. Okay. Divided by 0.25 no, it's times, isn't it? Times 0.25 equals x. Can someone do that, just so that we complete that calculation? Please, I just grabbed those numbers randomly. Just on that note, a number of people that repeat this subject, through different reasons, they often do very, very well the second time round. And when it comes to looking for jobs, there's not much at Unitec you can actually throw at an employer. One thing's plans. You wouldn't kind of give them a maths exam and say, look at that, or a survey exam or anything like that. One thing you can do is throw plans at them. They're usually not going to ask how many times you've done something or what was your mark the first time round, because they just want to know what level you're at now. So a B looks a hell of a lot better than, say, a C minus for those that have squeaked through and they're going, yes, I passed. A B or an A looks a lot better than a C minus. So, and also, when you've finished your drawings, don't throw them away, because the other little tip I'm going to give you is that I usually give feedback or some sort of model answer. If you copy my model answer and you add to your drawing and make it look quite spectacular, and you've done all the work yourself, I can't exactly say to the employer that that wasn't your work. All right, but you can present them with some pretty spectacular drawings to try and get a job. mostly talking to the engineers here. Surveyors don't usually have that issue in Auckland because there's a big lack of them. But yeah, a lot of students have done that. They've gone away in the holidays and they've tarted up their drawings so they look really, really good. And then they've taken them into a job interview, which is fine by me. Okay, did someone do this X for me? No?
Student fee is opposite.
Oh,
That is the correct?
this one here.
Yeah, because the 0.25 should be below.
Do I put 0.25? So what are you saying it should be?
It should be at the denominator.
Should be x is equals to 20.26.
X, start again. X equals. X should be over the.
No,
No,
that's
x equals 0.25
0.25
times 20.26 over 0.28.
which equals
13.329.
329 or 33?
33.
33, all right, okay. X, I like the people that are very accurate like that. 13.33. Okay, sorry. I got a bit muddled up there. But anyway, you all happy with that? It looks about right too. Then always sort of double back and check these things as well. In actual fact, we've done the X back the other way, haven't we? Yeah. So we okay, so that it's not confusing when you come to calculate it, we've actually calculated X that way. 13.33. Okay? Because we put the triangle at the top, coming backwards from 101. And when you think about it, the difference between these levels is 0.25 here and 13.13 that way. So it's always going to be a longer distance that way than it is that way. That's the calculation method. Now the fun starts. That was the easy bit. The reason why I do this in the lecture is that it means otherwise I've got two classes that I'm teaching in labs, and it means I'm going to have to do it twice in the lab, which seems silly if I can do it once for you guys now. Okay, let's do 19, 20, 21, 22, 23, 24, 25. So these are existing contours. They're relatively even, but they're not perfectly even. Um, 18, 17, 16, 15, 14, 13, 12, 11, 10. We're going to do design contours now in terms of a platform. We're going to use the same criteria as the assignment. So cut is 1:1, fill is 1:2. We don't have AutoCAD here. We're doing it on a whiteboard. So I'm going to make myself up a little wee thing here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10, 1, 2, 3, 4, 5, and 0. So that's just so I can do some measurements in terms of meters. Basically, we have a platform that is on a bank sloping down like that. The 1 to 2 is going to be something like that. The 1 to 1 is going to be a lot steeper, up like that. Okay? Platform is this piece here, which is this bit here. Very similar to your assignment. The first thing that we need to ascertain is what's cut and what's filled. Well, the cut side of the platform is going to be where the existing ground, this is existing ground here, where the existing ground is going to be higher than the platform. So the cut is going to be on this side, it's going to be cut. And the fill is going to be where the existing ground is lower than the platform, so over here is going to be our fill. So that's the first thing we do with our platform design. Sometimes I get students hand in assignment 2 and that's the only thing they do is those 2 words, which means they've learned something, which is good. The next thing we need to do is to try and work out what this portion 1 to 1 and 1 to 2 means. When we give a slope grade or portion like that, what we mean is that for every time we go out 1, we go down 1. So if I go out a half a step, I'm going down half a step. If I go out 2 steps, then I'm going down 2 steps. So it's very proportional. If I go out 0.3, I go down 0.3. If I go out 0.1267, I go down